Hello, this is going to be a screencast for the Mousetrap Car Project. So let's get to the thing. Oops. Okay, so this is my car right here. This is going to be just a video. I'm just going to play it for proof if that's needed. It goes. Good for my car. Let's see that again. Alright, cool. So now let's move into something else. Let's go to... Oh, not right now. Okay. So what we want to do right now is using that data, or using that video what we got, is we put that video into Tracker, and what Tracker did is it found all the points for the movement of the car. So what it did is it tracked the car, recorded how fast it went at different times based on the different variables I gave it, like velocity or displacement, stuff like that. Okay, I don't have that with me right now, and you're not looking at it because I was not able to download Tracker on this computer. Okay, but from that we can just take the data that we got from there and copy paste it into Logger Pro. So with that you get two different graphs, a position versus time graph and a velocity versus time graph for your car. Okay, this is the position versus time graph, and this one's the velocity versus time graph. So as you can see here, you have two curves here, a single curve here, and then a curve at the very back here. What this signifies is that there are two accelerations, one when the car starts movement, and then one when it ends movement. These are the two accelerations that are used for the car. Same thing on a lesser scale can be seen for the velocity. It's on a lesser scale because tracking the car was, not perfect, but it's okay. So we get many things from these two graphs, which I'll explain. So I'm going to start in order so that we're not confused. This will be in order from the rubric. Okay, so I just showed proof of building my own mousetrap car. That's cool. Okay, now energy stored in a mousetrap spring. Okay, we did this using this graph, which was used with the torque. What's it called? The torque circle, something like that. But what we basically did is we took that thing and put a force sensor on the end of a piece of string and pulled it back and measured the force for each different interval that was pulled back. And based on that, we could find the force for that interval and all that stuff. And we could find the here what we found. After we got all those points, it made a triangle like this, or I mean a trapezoid. I'm sorry, a trapezoid. So we could find the area under that graph to get the spring constant, which was 0.386. Okay, using the spring constant, we can find the elastic energy of the car before it stopped moving. I'm getting a little bit ahead of myself, but this will be what is used to find the energy stored in the mousetrap, which is the very first item on the rubric. Next, we have the position versus time graph, which I showed you is this one right here. This is my position versus time graph. You can see the two different curves. The displacement of the mousetrap car. This would be the same thing as we can see here. The position, which is displacement, is here on the y-axis. You can see as time progresses, the displacement, which is position, slowly moves up. So as time progresses, displacement moves up. Okay. Next we have the mass of the mousetrap car. There isn't really much to show here. I basically weighed the car and then transferred its weight into kilograms, and its weight is approximately 0.104 kilograms. Okay, so just 0.104 kg. Okay, now we get the maximum velocity and kinetic energy of the Mousetrap car. The maximum velocity can be seen using the velocity graph. My velocity graph is in inches by seconds because when I put my car into tractor, my point of reference was inches, so I had to stick with that throughout. Okay, it shouldn't really matter. It's just a you know just a unit of measurement that doesn't really matter. It can be changed. Okay, so we have our inches versus inches over time, and basically our highest point in this whole graph is going to be the maximum velocity, which is right here. Clicking on this like so, we can find that this number right here is the number with the highest velocity. And as we can see, it's 31.9 inches per second. Okay, so we have that done. Now we need the kinetic energy of the Mousetrap car. Okay, we already know the mass of the car, which is 0.104 kilograms, and we know the velocity at this point, which is 31.9329. Okay, and the formula for kinetic energy is 1/2 mass times velocity squared. I did that in my lab book, which I don't have a picture of to show you, but then I can just give you the answer, which is 52.92 kilogram, or 52.92 joules is the kinetic energy of the Mousetrap car. Okay, moving on. We get the acceleration of the Mousetrap car during speeding up, and then acceleration during slowing down. Okay, this is the speeding up part. This is the slowing down part. Okay, to find these, all you have to know is that the slope of this graph, or this point in the graph, and this point also is the acceleration of that segment. So what I've done here is I've basically just taken and isolated this segment, also this segment. I can just find the slope of these two segments, and then whatever the slope is the acceleration of those 2 points. And the units are also correct because it says 25.3 inches per second, which translates to 25.3 inches per second squared. Same thing over here, just negative because it's slowing down and stopping instead of speeding up. Okay, then we have the total force, the net force, and or the sum of forces acting on the car. Okay, where have I found this? This is actually also in my lab book, but what we have here is that we know that for the speeding up part, normal force and weight cancel out. That's a given, 100%. Okay, but then for the speeding up, we know that there's a force of friction acting this way on the car, but then the force of the spring is acting this way on it because this is the way it moves. So we have to decide which way is the sum of forces. It's obviously got to be this way because this is the way the car starts to move and accelerate. Okay, so we already know that the force of the spring is 103.34. Okay, and we know that the sum of forces is MA. Okay, so the two arrows, let me go into paint real quick. Okay, here we are. 1 second, it's just, okay, here we go. Okay, so you have, okay, this cancels out with this. This is normal force, this is weight. Okay, then we have coefficient, or this is this is EL basically. Okay, this is the force in EL. Okay, and here we have the force of friction, and this is your sum of forces. Okay, so this is what we need for this point in the segment. Okay, but we already know that this and this, and this. Like these two arrows, which is E, F, and friction, have to equal this arrow. And this arrow is 103.34. Okay? And then we know that it's M. The sum of forces is MA, as MA. F. Okay? So M is 0.104 times acceleration, which is 25. So then through this, you can find this, which is really not needed because you just multiply these two out and you get that. When you multiply these two out, you get that the sum of forces equals 2.6 newtons. Okay? That's the sum of forces of the speeding up. Now, for the reverse, the same thing also applies. It has to be 2.6 newtons also, which is because new page, file, new. Okay, so for some forces slowing down, we have weight, and then we have friction acting this way, and then normal. These cancel out. Okay, but then the problem here is that there's no bouncing force going this way. This doesn't exist. So this is your sum of forces, and this is friction. Okay, so EF equals F. Okay, we already know that EF equals 2.6 equals friction. So 2.6 is your force acting on it backwards to 2.6 newtons. Okay, so that's that. Alright, so that's my video on my car. These are the graphs, 2 accelerations, found out all that I can about it. This is my video once again, if you'd like to see it. Whee! It's a lovely car. Okay, it's my data I use to get my spring constant. And these are my beautiful graphs. Thank you very much for watching, and I hope you learned something.